Hello, this video covers the lecture part of Lab 7, which is about Laplace transform. In Lab 7, we're going to learn briefly the concept of Laplace transform, and then we're going to learn how to plot each of the step response, the impulse response, the zero-pole diagram, and the ball plot of a transfer function. Finally, we're going to learn how to find the zeros, poles, and gain, as well as the residues and the direct terms of a transfer function, with the help of MATLAB, of course. Basically, Laplace transform transforms a function from a real variable into a complex variable named s, and it's commonly used to help us simplify calculations. Here's a table that lists some of the commonly used functions and their Laplace transform. You will use this table to help you solve some of the exercises in Lab 7. Now we're going to move on to an example in which we're required to plot the impulse and the step response of a given transfer function. So the first step is to find the coefficients of the numerator of the transfer function and store them in an array named, for example, num. So we're going to do that for the numerator. We only have one coefficient, which is 2. And now for the denominator polynomial, we're going to also do the same thing. We're going to store the denominator coefficients in a variable named denominator, and we're going to put the coefficients of the highest power first. So the highest power is s squared, or 2. So the coefficient of s squared is 1. Next, we have the coefficient of s, right, which is 2. Finally, we have the coefficient of s raised to the power 0, which is 3. So we're going to store these numbers in an array named denominator. And the next commands are very straightforward and simple. First, we're going to type the keyword figure to help us open a new figure window in MATLAB. Next, we're going to write the command that will help us, or the function that will do the plotting for us. To plot the impulse response, you can simply type impulse, and then as impulse, you're going to pass the numerator array, the numerator coefficients array, and the denominator coefficients. Next, we're going to again type the keyword figure, just so that we don't override the impulse response figure, but rather open a new separate window for the next plotting command. So we're going to type figure once again. Next, to plot the step response, the function is very straightforward. Again, it's simply just step, and it takes 2 inputs. The first input is the coefficients of the numerator, then the coefficients of the denominator stored in an array. Now we're going to do another example of the same thing, of plotting the impulse and the step response of a given transfer function. We're going to repeat the same steps, but this time we have a different transfer function. For the numerator, we only have 3, so we can write simply numerator is equal to 3. For the denominator, we have the coefficients 1 for s squared, and then we have 1 again for s raised to the power 1. For s raised to the power 0, the coefficient doesn't exist, so we can assume a 0 in place of it. So the denominator coefficients are going to simply be 1, 1, 0, stored in an array. The next step is to type figure, so we can open a new figure window, and then we're going to type impulse, numerator, comma, denominator, so we can plot the impulse response. Next, before calling the command to plot the step response, we're going to open another new figure window by typing figure in MATLAB. Then we're going to simply type step and pass the numerator array and the denominator array as an input to the step function. Here we have one more example. We'll simply assign 2 for the numerator. Then for the denominator, we have 1 as the coefficient for s raised to the power 3. And then notice that s squared is missing, so we're going to assume a 0 in place of it. So there is 0 times s raised to the power 2. And then s to the power 1 is also missing, so we're going to assume that the coefficient of it is actually 0. And then we have 1 s raised to the power 0. Because s raised to the power 0 is simply 1, so the constant will be the rightmost element in the array of the denominator. So the denominator can be simply assigned a value equals to 1, 0, 0, then 1. Next, we can simply call the impulse function. But before that, we're going to open a new figure window. So we're going to type figure, then impulse, numerator, denominator. Then figure again to open a new window, then numerator, denominator. Step, of course, to plot the step response. And we're going to pass the numerator and the denominator as inputs. Here we have an additional example. Observe that the numerator is simply 2. For the denominator, we have 1, 2, 3, right? So there's no zeros at all because we start with s0 and its coefficient is 3. Then we have s1, s raised to the power 1, and its coefficient is 2. And next we have s raised to the power square, and its coefficient is simply 1. Next we're going to type figure to open a new figure window. Then we're going to call the function step or impulse first to plot the impulse response. And finally we're going to type figure again to open a new figure window. Finally we're going to call step to plot the step response. Now we're going to move on to a new example in which we're required to find the zeros, poles, and gain of a transfer function. And we're also required to plot the zero pole diagram and then to plot the pod plot of the transfer function. So there's actually 3 parts into this question, but for all of them it is important that we first create the numerator array, so an array for the coefficients of the numerator. For this example it's going to be 2 and 3, so these are the coefficients of the numerator. For the denominator it's going to be 1, 4, 0, 5. Notice that there is no coefficient for s, that's why that means it's 0, so in place of it we're going to put a 0. So to answer all of the 3 parts in the question, it is important that you define the numerator and the denominator arrays first, and then simply for answering the first part, which is finding the zeros, poles, and gain, we can simply call the transfer to zero pole function, and it takes 2 inputs, the numerator array and the denominator coefficients array. Notice that this function outputs an array of output, meaning it has more than one output, which are the zeros, pole, and gain arrays, meaning it's important to, when calling this function, it's important to assign variables or the output a variable name. This way you won't lose it. And it's important to also recognize the order of the outputs. So it's always going to be the zeros first, then the poles, and then the gain. And in case you forget the order, you can always refer to the help command in MATLAB by simply typing help in the command window and then followed by a space, followed by the name of the function. In this case, it's going to be TF2ZB. Remember, this is simply short for transfer to zero pole, so you don't forget it. In the next part, we're required to plot the zero pole diagram. So the next command is gonna create a new figure or plot something for us. So for that, we're gonna allocate space for it by simply typing figure in order to open a new figure window. It helps to do that, but here we didn't. We assumed that it's our first plot. Then the next step is to call the plotting function, which is bzmap. So bzmap is the function to call when we want to plot the zero pole diagram of a Laplace transform function. Next, to plot the pod plot, the function is simply pod, but before it we're going to type figure to open a new figure window. This way we want to overwrite the zero-ball diagram. Next, we're going to type simply pod and provide the two inputs for the plot function as the numerator coefficients array and then the coefficients of the denominator. Now we're going to solve another example in which we're required to find the zeros, balls, and gain of a given transfer function. Again, we're going to simply create a variable named numerator in which we're going to store the coefficients of the numerator polynomial, which are going to be 2 and 1. The next step, we're going to create an array or variable named denominator in which we're going to store the coefficients of the denominator polynomial, which are going to be 1, 3, -4, and finally 0. Notice that the constant is missing from the denominator polynomial. This way, in place of it, we're going to put a 0. The next step is to simply call transfer to zero-ball function and provide the numerator and the denominator as inputs. And also notice here we're assigning values to the output or variables actually for the output names, so that we have the zero arrays, the zeros array first, then the poles, and finally the gain. Again, if you miss on the order or you forget about the order of the output, you can always refer to the help command in MATLAB. So if you hit enter or if you run the script file containing these 3 lines of code in MATLAB, you're going to receive this output at the command window. So with the help of this output, we can rewrite the given transfer function into a different form, which you can also find it in the help command if you simply type help transfer to zero-ball in MATLAB. So let's do that. We're going to rewrite h of s in a different form following this format right here. So we're going to simply say h of s is equal to s minus the first 0, which is minus half, so it will be plus 0.5. We don't have any other zeros, so we can ignore these terms. Next, we're going to create the denominator, and it's simply going to be s minus the first pole, which is 0, so I'm going to ignore the subtraction here. Next, I'm going to continue with this term, so it's going to be s minus the second pole, which is here, so it will be plus 4. And finally, we have s again minus the last pole, which is 1. Finally, for the gain, we can simply multiply the gain by everything we have in here. So now what we've done is we've used the transfer to zero-ball function or command in MATLAB to help us obtain the zeros, poles, and gain, so that we can rewrite the transfer function from this form into this form on the right hand side. Now we're going to do another example, but this time we're required to find the residues, poles, and direct terms of the given transfer function, and then we're required to use the results of the residues, poles, and direct terms in order to find the partial fraction decomposition of h of s, and finally we're required to find h of t. So there are 3 parts to this question. We're going to start with the first part, which is finding the residues, poles, and direct terms, and these are all actually can be found using one function called in MATLAB. But again, first we need to define the coefficients of the numerator polynomial. So it's going to be numerator is equal to 1, -5. Denominator is going to be equal to 1, -4, 3. Now, to find the residues, poles, and direct terms, the function to call is simply residue, and it will take the numerator and the denominator as inputs, and it will output the residues array, the poles array, and finally the direct terms array in that exact order. Again, to help you remember the order, you can always use the help command in MATLAB on the residue function. So you can type help residue in the command window, and it will provide you with details on how to use it and the order of the output and so on. Now moving on to the next part of the question. Again, if you hit enter or run the script file containing these three lines of code in MATLAB, you're gonna end up with these results. So you have an array containing the residues, an array containing the poles, and it will have an empty array of direct terms. With the help of the command window in MATLAB, you can also find the way to help you transition or transform the transfer function from this format into the partial fraction decomposition. So this is the partial fraction decomposition format, and we're going to use the output of the residue function to help us rewrite the transfer function into partial fraction decomposition form. So we can say that h of s is equal to the first residue, which is -1, divided by s minus the first pole, which is 3. Then we have plus the second residue, which is 2, divided by s minus the second pole, which is 1. And you're going to continue until you're done, but we're done now, so we can stop here actually. Now to complete the last part of the question, which is finding h of t, we're going to refer back to the table we saw earlier. This is what we've derived in the previous slide. So now with the help of the table, we're going to find h of t, or the inverse of Laplace transform. So from the table, we're going to look up something that looks similar to this term, which is right here. And now our a in the partial fraction decomposition for this term is actually 3, right? So we can say that a is equal to 3, because in the denominator we have s minus a, and here we have s minus 3. That means a is equal to 3, right? So to write the signal itself, h of t, we're going to start with negative, because we have here -1, and then simply e to the at, and a is 3, and then ut. Next, we're going to say plus, and then continue with the term on the right hand side. It also follows the same format, so we can simply use the same row here from the table to help us write h of t. So we can simply say plus 2 e for this term. We're going to raise it to the power t simply because a is actually 1, right? So now it'll be 2 times e raised to the power t, and then ut. So now we've solved the entire question, including finding h of t. Most of the questions part, to solve them, we've used MATLAB functions, except for finding h of t. With the help of the residue function, we're able to find the partial fraction decomposition first for the second part, and finally with the help of this table we're able to find h of t. What you see here now is the output in the command window. If you type help residue, there's 2 things I want to highlight here. First is how to rewrite the partial fraction decomposition of any given transfer function with the help help of the residue function. And next, how to write the partial fraction decomposition in case of having repeated poles. Notice that it's very similar to the one with non-repeated poles, except you're going to square the denominator every time you have a repeated pole, and then raise it to the power 3 the third time it's repeated, and so on. We're going to see an example in the next slide to help you better understand the case of repeated poles and how to write the partial fraction decomposition. So here we have an example again of a transfer function with repeated poles, and we're required to find the partial fraction expansion of it with the help of the residue command in MATLAB. So we can simply again write the numerator coefficients, which is going to be numerator is equal to 4, 0, 4, 1. Notice that s squared term is missing from the numerator. That's why in place of it we put a 0, because its coefficient is 0. Now for the denominator, we're going to write 1, 3, 2, 1, and then finally 0, because there is no constant in the denominator, so in place of it we're going to put a 0. The next step is to simply call residue, but make sure you assign a variable for each of the outputs. So we have R, P, K in that exact order, and then we type residue, and then as inputs we're going to pass the numerator array and the denominator array. If you run the script in MATLAB, this is what you see. This is what you're going to see at the output. So we have here actually 3 repeated poles and 1 that's not repeated. So to write the partial fraction decomposition in case of a repeated pole, what you're going to do is, as mentioned earlier, is you're going to square each time you use a repeated pole. You're going to raise it to the power 2. Then the third time you use it, you're going to raise it to the power 3. The fourth time you use it, you're going to raise it to power 4, and so on. So let's do this example to help emphasize your learning on it. So we're going to rewrite h of s that's provided to us as a partial fraction decomposition. So we can simply say h of s is equal to the first residue, which is 3, divided by s minus the first pole, which is 1. So which is negative 1 actually. So we're gonna do plus 1 instead. And then for the next term we have plus. It's negative 9, the second residue, divided by s minus the second pole, which is negative 1. So that will be s plus 1. Since we've used s plus 1 before, or we've used this pole before once, so that means the second time we're going to use it in the denominator, we're going to square the entire denominator together. Next, for the next term, we have plus. In the numerator, we have 7, the third residue. In the denominator, again, we have s minus the third pole, which is minus 1. So that will convert into plus 1. But notice we've used s plus 1 before, and the power of it was 2, so this time it's going to be raised to the power 3. The next term is going to be the fourth residue in the numerator, so it's 1, divided by s minus 0. So we don't have we can say s minus 0, or we can simply erase s minus. It will simply be 1 over s, because s minus 0 is simply s. We don't have again, so we can, or direct term, so we can stop here actually. So that completes the finding of the partial fraction expansion of the given h of s. This slide summarizes some of the commands needed for today's lab. First step is to remember to write the coefficients of the transfer function for the numerator polynomial and the denominator polynomial, and remember to put them in order. And if there's any term that's missing, for example, if s squared is missing or the constant is missing, you need to put a 0 in place of its coefficient. Next, to plot the step response, this function is simply step, and it takes the numerator and the denominator as inputs. If your code requires you to plot more than once, remember to use the keyword figure to open a new figure window each time you want to plot something. Next, to plot the impulse response, you can simply call impulse. To plot the pod plot, you can call pod. And to find the zeros, poles, and gain, you can call transfer to ZP. And make sure you provide the numerator and the denominator as inputs. And make sure you assign variables or names for the output of the transfer to zero pole function in that exact order. It starts at 0, then pole, then gain. Next is finding the residues, poles, and direct terms. To do that, you need to call the residue function, and the output is exactly in that order. And if you're also required to find the partial fraction decomposition of a transfer function, you can simply call residue and follow the steps we've explained previously in order to find to rewrite h of s in terms of partial fraction expansion. Finally, to plot the zero pole diagram, you can call pzmap. This concludes the lecture part of Lab 7. If you're watching this during a live lab session and you have questions, please type them in the chat. Otherwise, you may email me at al@auk.edu.kw.